All right, this is day 1. We're just going to do a little bit of notes today. 3.2. Two big ideas in this lesson. Something called conditional probabilities. That's what we'll talk about today. And then independent and dependent events. And then something called the multiplication rule. Okay, so chapter 3 is all about like the basics of probability. In 3.1, we just kind of talked about different types of situations and our general rule for our classic probability, number of possible ways something, an event can happen over the total numbers of ways something can happen. So like what's the probability of drawing out a card that's a 3 out of a deck of cards? There's 4 3s in a deck out of 52 total cards, something like that. Okay, so conditional probability is basically you're trying to figure out the probability of something given that another event has already occurred. So kind of given like a condition almost. The notation we use for this is we still do like the probability of something happening, but we already know that an event happened. So let's say I want to know the probability that event B has happened, given that, so use a vertical line for that, given that another event has already happened. Okay, so how you read this statement out loud is the probability of event B happening, probability of B, given that A already happened, given A. The probability of B given A. That's what we call conditional probability, and obviously with a couple examples. One other thing I want you to write here, technically like the formula for finding this probability, I only use this when it's like fitting, because sometimes you can just logic your way through it. You have to find the probability of both events occurring, and you're just going to divide it by the probability of that A already occurred. Okay. So here's like an example of a conditional probability. 2 cards are selected in a sequence from a standard deck of 52 playing cards. Find the probability that the second card is a queen, given that the first card was a king that you drew. Assume the king is not replaced. Okay, so here's an example. I'm going to find the probability that the second card is a queen, given that the first card is a king. Okay, so I don't really, like I said, use that formula a whole lot. I kind of just logic my way through that. So I asked myself, how many number of queens are left divided by my total number of cards left? And the only condition you have to remember is we no longer have 52 cards left. Since I drew a king and it's not replaced, how many cards do I really have left? 51. Does that change how many number of queens are in the deck? No, it would have if the first card I drew was a king, was a queen. Then I'd have to factor in that condition. But because there's still 4 cards left in a queen, 4 out of 51, or as a decimal. Okay, so there's a pretty like textbook classic definition of or example of oh my gosh, I can't talk. Conditional probability. I'm also really tired. Conditional probability. All right, let's look at some more Alex types of problems with conditional probability. This one gives you a nice visual of like selecting some possible outcomes and tying it into the conditional probability. So here's our example here. Suppose that the genders of the 3 children of a family are soon to be revealed. An outcome is represented by a string of the sort GBB, meaning the oldest child to be girl, and then boy, boy. So the 8 possible outcomes are listed in this table. Assume that each outcome has the same probability. Complete the following and write your answers fractions. All right, so we have these different events that they want us to check our possible outcomes, and then we'll write the probability. So event X, they're saying, which of the outcomes is the last child a boy? So looking through my list here, this one, last child's a boy, this one, this one, so 4 out of 8, so 1/2. Leave it as a fraction. So I have a probability of 1/2, or like 50% probability that the last child is a boy. For the 3 kids. All right, new event says exactly 1 child is a girl. So look at my list of outcomes. This one, there's 2 girls, exactly 1 girl. 3 out of 8. Okay, event X and Y combines these 2 events so that the last child is a boy and exactly 1 child is a girl. So from my options of the last one that's a boy and exactly 1 girl would be this one. Last one's a boy, exactly 1 girl. This one. Only 2 out of 8 or 1/4. Okay. All right, so this follow-up question says, suppose exactly 1 child is a girl. So suppose this is like given information. So we know event Y occurs. It's given that exactly 1 child is a girl. This limits our possible outcome. Example conditional probability. Here's your condition. Exactly 1 child is a girl. So now, similar to the deck of cards, and I was only left with 51. Now I'm only left with 3 options. So from the remaining outcomes, check the outcomes for event X, which that was our one that the last child is a boy. Okay, that'd be this one and this one. So my new probability is 2 out of how many? 3 are my only possible outcomes. Okay, now here's kind of like that little formula I showed you, that the conditional probability will get the same as taking the probability of both occurring divided by the probability that the given event already occurred. So let's take our data from our first table here, the probability of X and Y. That was my blue one here. This is right here. This is the probability of X and Y occurring. Is 1/4. So there's 1/4. If I divide that by the probability of Y happening, which I think that was our green one. Let's go ahead and write all these in. This is the probability of X, probability of Y, probability of X and Y. All right, so divide it by 3/8. Yay, finally some mathy stuff here. I don't like to divide fractions. I like to times by reciprocals. Keep the first fraction, change it to a multiplication problem. Flip the one you're dividing by. I tell my students keep, change, flip. Let me do these in Algebra 2 with variables and stuff. We can reduce this. I like to cancel before I multiply. Common factors. We get 2/3. And you see that's the same probability I got with this condition. What's the probability that event X occurs given that Y's already occurred? Was also 2/3. Okay, so that conditional probability is equal to the probability of both events happening. That was that little formula I had you write down before, divided by the probability that Y already occurred. Both are 2/3. Anything else I need to tell you about that one? I don't think so. Okay, we're just gonna try a few more. All right. Here's another example. 8 balls numbered from 1 to 10 are placed in a bed. Some are gray and some are white. Hopefully you can kind of see which ones are sketched gray. Yeah. A ball will be randomly selected. Answer the following questions, write each as a fraction. What is the probability that the ball selected is white? All right, so straight up just classical probability. Number of white marbles, 4. Out of total number of marbles, 8. Reduce that to 1/2. Okay, that's kind of like a review of what we talked about last lesson. B. Note how B gives us a condition. It says, what is the probability that the selected ball is white given that an even number ball is selected? So basically this condition just kind of limits some of our possible outcomes. It's given that our even number ball is, or that our ball is an even number, so it can't be one of these odd numbers. I kind of like to cross them off. So now to find the probability that it's white, I only have 1 out of my 4 possible even numbers. There's an example of conditional probability. Oh, I like this next one. It's so fun. What if I was given, instead of like a visual like this, what if I was given a chart? So Dr. Foster is a veterinarian who sees only dogs and cats. In each appointment, he may or may not give the animal a vaccine. The two-way frequency table summarizes Dr. Foster's 50 appointments last week. Let vaccine be the event that a randomly chosen appointment from the table included a vaccine, and let dog be the event that a randomly chosen appointment from the table involved a dog. Find the following probabilities. Write your answers as decimals this time. Okay, so the probability that the selected animal was one that was like vaccinated or got the vaccine. So looking here at my number of animals that got a vaccine, I had 12 dogs and 18 cats. So I had 30 total animals get the vaccine out of how many appointments? 50. As a decimal, that's 0.6. 6 times. Okay, it's kind of more like a classical. This one is an event that includes both. What's the probability that the selected animal was a dog and it received the vaccine? That'd be just these 12 out of my total 50. So that'd be 0.24. Okay, I like this one because it has a notation with conditional probability. So no, this is not the same as and. This is saying, find the probability that the selected animal was a dog, given that we know it had the vaccine. I'm just going to write that out. Given okay, so basically what this eliminates from my total possible outcomes are these ones. We know that it received the vaccine. So out of these, 12 plus 18, out of these 30, out of these 30, what's the probability that from these 30 I select a dog? 12 out of 30, which is 0.4. You could also write this out too if you want. 12 over, you got the 12 plus 18, that's where that 30 came from if you need that reference in your notes. Okay. See the difference? Good. Good, good, good. Let's try one more conditional probability. And I'll briefly talk over one other thing. Okay, this time our data is just kind of presented to us in a different way. No nice little marble diagram, no chart, just some information. It says it's estimated that 30% of all adults in the U.S. invest in stocks, and that 85% of U.S. adults have invested in fixed income instruments, savings accounts, bonds, etc. It is also estimated that 26% of U.S. adults have investments in both stocks and fixed income. Okay, I'm going to kind of write this out like in math notation. So 30% of all adults in the U.S. are invested in stocks. So the probability that a U.S. adult randomly selected is investing in stocks is 30%. I'm going to write it as a decimal. The probability that a selected adult has some fixed income, such as a savings account, I'm just going to do F, is 85%, so 0.85. And the probability that they have both, so stocks and a fixed income, is 0.26. Okay, so 2 questions here you need to answer. A says, what is the probability that a randomly chosen stock investor also invests in fixed income instruments? So here's kind of the notation. What's the probability, given that the person chosen is a stock investor, so the given always comes second. So we know he's a stock investor. What's the probability that they also have a fixed income instrument? It's not just that 0.26 number. It's this condition. What's the probability that we know it's a stock investor, also does a fixed income? So you got to take, the probability of having both, which is 0.26, that many percent, out of my total population of just investing in the stocks, 0.3. So it's about an 87% chance. So basically, like out of this set of population, out of that set of population, what's the likelihood that they have both? Well, according to our data, 0.6 out of that. Or again, here's like a little formula, but the probability of both divided by the probability that's given. If that formula helps you set these up, you can do that too. Okay, so this one's a little bit different, the next one. What's the probability that a randomly chosen U.S. adult invested in stocks, given that he or she invests in fixed income instruments? Okay, so now I want to know the probability that my randomly selected one is involved in stocks, given that they do have that fixed income instrument already. Okay, so what's given to us is that they already have a fixed instrument. So my kind of like total population here is at 0.85. And then, so from that, what's the likelihood or the probability that they're also a stock investor? So for both, 0.26 divided by that.
Excuse the interruption. Cameron Ashe, Orlando Padilla, Madden Krubel, Jordan Coleman, Ilona Lee Griffin, and James Napier, please report to the conference room. That's Cameron Ashe, Orlando Padilla, Madden Krubel, Jordan Coleman, Ilona Lee Griffin, and James Napier.
Okay. Last thing I want to talk about, and then we'll stop here. Tomorrow we'll get into like independent and dependent events because that introduces us to this multiplication rule. So just a quick overview of what these are. When one event does not affect the probability of another event happening, we call those like independent events. So like, for example, if you roll a dice and toss a coin, the outcome of the dice does not affect the toss of the coin. That would be an independent. And then if 2 events are dependent is when the occurrence of one affects the probability of the other. So like a really classic example of this is like if you're drawing out of a card and you don't replace it, what happens in the first draw affects the likelihood of your second draw. That's like called a dependent event. Okay? We'll leave off there. You guys think that's enough for Monday?
Yes.
Yeah.
Great. Got to elaborate.
Yeah, we did.
All right, so here's the plan. We will finish these notes tomorrow.